All right, hi everybody. So thanks for the introduction, Aaron. I'm going to be talking, like Aaron said, about programming language technology for the sciences. Before I get going, how many of everybody in the audience recognize these people, Reinhart and Rogoff? All right, very small number. Okay, so these two folks are Harvard economists, and they wrote a very influential working paper called "Growth in a Time of Debt." And the sort of central result of this working paper was this notion that once you cross this threshold, if you have some, you've got your country and it's got its economy running, and there's a certain amount of debt over GDP ratio. And what they discovered, or what they claimed to discover, is that once that GDP ratio crossed 90%, then economies would enter into this death spiral. Where they would just enter into sort of a place where they could never recover. The economic growth just stays low and gets lower and lower. All right? So this was quite influential. It was used in the United States by certain politicians to justify their budgets. It was also especially influential in Europe, where it was met with great fanfare, fires in the streets. This is a scene from Greece. Basically, the point is that this was used to justify austerity budgets. So, as you can imagine, this is a kind of thing that required lots of analysis. So you might ask yourself, well, how did they do this analysis? It's a complex analysis. So what programming language did Reinhart and Rogoff use to come up with these results? Right? So did they use C++? The answer is no, they did not use C++. It's a reasonable guess. It's a fairly widely used programming language. It has about 3.5 million users, but Reinhart and Rogoff are not among them. How about Java? Java. Java's a better guess. It turns out there's more users of Java than C++, but that's still not the right answer. So does anybody have a guess as to what the right answer might be? The right answer is Excel. So Excel is also, you might not think of it as a programming language, but it is a programming language. It has a very large number of users. 500 million is the estimated number of users of Excel, including 2 economists at Harvard. Just to put this into sort of sense of scale, this is 7% of the world population. So it's a huge, huge number of users. Really quite shocking. So this is an excerpt from their spreadsheet, which we were able to obtain. I asked both of them for the spreadsheet, and I got an angry letter back from one, and then I got the spreadsheet from the other, so that was good. So the spreadsheet became famous because it turns out that it wasn't exactly right. So Paul Krugman had this article that appeared in the New York Times, and it says, "The Excel Depression." And he asked this question, so did an Excel coding error destroy the economies of the Western world? The answer is no. The answer is actually that many, many errors destroyed the economies of the Western world. This is just a little snippet. These folks down here, and I'll talk about them more in detail, they turn out to be economists at my institution, the University of Massachusetts. And they did a very detailed analysis that took them some number of months to complete, and they discovered that, in fact, the results are not the results, when you correct this spreadsheet, not the results that Reinhart and Rogoff heralded. So you can see over here that the blue is the actual results from Reinhart and Rogoff spreadsheets, and they binned things up into these different categories of debt and GDP ratio. The red is corrected. Here's the death spiral. Here's the reality. Oops. So the question is, really, is this something that we could have prevented? Right? So, Reinhart and Rogoff did this. You might think, oh, those silly Harvard economists, what do they know? But it turns out it's actually really, really hard to see all of the problems that eventually were revealed in this giant spreadsheet, as I'll show you. So, programming languages and computer science in general have long been used in support of the sciences, right? And so here you have a shot of, on the left is the wonderful Barcelona Supercomputing Center, which is housed inside of a church, former church, right? kind of a weird religion there, I guess. And another supercomputing center, I think, is Sandia. This is really, the traditional domain of computer science in the support of the hard sciences. But the soft sciences are different. The soft sciences have a number of different challenges that make it much more complex, or really sort of a completely different problem to support. And they use different tools. Right? So, it turns out that spreadsheets are widely used across the social sciences, not just by everybody practically in the world, but social sciences use spreadsheets as well as this other tool, which is surveys, to do their science. And of course, they're not just used for social science. Excel is widely used. Spreadsheets are also ubiquitous, right? These are things that are used by 7% of the world's population. There's at least 20 million users of web-based survey programs. How many of you have taken a survey on the web? All right, so the people with their hands down are doing something else like texting. But everybody clearly has done this, right? So they're incredibly widely used across a ton of domains, right? So not just for economics, but for education, for government, for policy, all of these sorts of things. So what I'm going to talk to you today about is two things that we built to address these issues. There's plenty to do in this domain. This is just our first two efforts. I'm going to talk about something that we built to find problems in spreadsheets that we call CheckCell, and something to address issues in surveys, which I'll explain in detail, called SurveyMan. All right, so I'm going to start with CheckCell. So here's this snippet from this spreadsheet from Reinhart and Rogoff. And like I said, it's a really big spreadsheet. So what could go wrong? Right, so you have a spreadsheet, and you think to yourself, well, what could go wrong? Well, it turns out people make mistakes. This is a Harvard economist right here. So Harvard economists make mistakes, and ordinary people do too. So just like in computer programs, right, Excel is a kind of computer program. Your program could be wrong, right? And if your program is wrong, probably won't get the right results. Your inputs could be wrong, right? Garbage in, garbage out. And in spreadsheets, notably in the Reinhart-Rogoff spreadsheet, both could be wrong. All right? So obviously, inputs are a huge problem. So when people are typing things, they make mistakes. So it turns out, and this is something that we validated ourselves independently, but these are numbers that seem to hold true, at least 1% of the characters that people type are wrong. Now, 1% may seem like a low number, but when you have thousands and thousands of numbers that are being entered, it's actually a pretty high rate. And this translates to about 5% of cells being mistyped. So that means really, if you have a spreadsheet above any reasonable size, you're virtually guaranteed that there's some typographical error. All right? And of course, this is, like I said before, not the only source of errors. There's all these other program errors. So one of the things about spreadsheets that's in a way nice is, and this is why people use spreadsheets, is that they allow you to intermingle data and formulas. In this Reinhart-Rogoff spreadsheet, there are so many formulas and data that it's mind-boggling. This is actually a collection of economic data spanning, you can see, I don't know if you can make it out, this is a date, these are all dates. This is 1791. So they collected economic data for over 100 years for most countries. I think they had about 26 countries. So they had all of these different sheets, all of these formulas spanning all of these sheets. It's really no surprise that it was hard to find mistakes. So what you would like, I think what I would like, would be something like Clippy, right, for spreadsheets. Like, it would be really nice if you were typing into a spreadsheet and Clippy came up and it said, something looks bad, right? So that would have been good. It could have saved a lot of burned cars. All right, so what are the problems? So the challenges, some of these challenges are the kind of traditional challenges that we always face when we're trying to analyze programs for correctness, but some of them are quite different. So as is usual in programs, in Excel spreadsheets, there's no spec. Right? There's no spec for here's the correct analysis of the economies of the world. Right? Everything is really, the spec is the code. You can't really do sort of traditional analysis and say, well, I'll just assume that there's some distribution and I'll find numbers or strings that look weird. This is not something really that you can do in general. You don't expect, for example, a normal distribution of numbers, just sort of arbitrary numbers that you type into Excel. And that means that you can't use all of these tools from statistics like outlier analysis. So that's really unfortunate. So what we do, what our tool CheckCell does, is that it combines, much in the way that, that was described by Martin in the previous talk, we combine program analysis and statistical analysis. So CheckCell actually analyzes the interaction of data and the formulas. So it doesn't just look at the data, it doesn't just look at the formulas, it looks at them both. And what it does is it identifies cells that have an unusually high impact on the results. That is to say, the outputs of the functions themselves. Right? And it turns out that if you identify things that have an unusually high impact on the results, really either they're very important, right? They have a tremendously high impact, or they're wrong. Right? They have this very high impact because there was something wrong in the data. So let's go back to a spreadsheet. Actually, this is not the Reinhart Rogoff spreadsheet. I'm going to have a working example based on this. This is actually a spreadsheet that we spidered from the web. It turns out that if you do a search for .xls or .xlsx, you find lots of spreadsheets. This is actually a grade spreadsheet that probably shouldn't be up on the web. And you can see it's quite large. It's pretty typical of the kind of spreadsheet you might have if you're managing a class. You've got a bunch of homeworks, and you've got different weights, and then you have total scores at the end. Auditing a giant, I'm sorry, whoa, that was interesting. Let's try that again. So auditing a giant spreadsheet like that is really hard. If you had a tiny, tiny spreadsheet, maybe it would be tractable. But here, I'm just going to use this as a working example. I extracted one student's information. And you can see here's a bunch of homeworks. Here's some quizzes. Here's some exams. There's different weights. So can you guys find the mistake? What's the mistake? Which one? What? Pass, fail. So, right, so this formula here, this is actually for a graduate class. You can't count a grad class. This is at least at the University of Massachusetts. It doesn't count towards your degree if you get below a B+. So here, this person sadly failed the class. So notwithstanding the issue of grad fail, if you look at the numbers, nothing looks particularly suspicious, right? All the numbers seem reasonable. And it turns out there is actually a mistake in this spreadsheet. So here, what I'm showing you is actually our CheckCell plugin. So CheckCell actually is a plugin that goes right into Excel. If you are running Windows, you can just download CheckCell and add it to Excel. You click Analyze, it goes and it looks for errors. And it turns out that this 78 actually is the most influential data element. And if you have a 78 here, that's going to lead the student to fail. And if 78 was just a transposition, which it is in this case, you can go ahead and fix it. It says, oh, I meant it to be an 87. And when you enter 87, all of a sudden the student passes. If you find, it then goes and finds other potential errors. You can say, no, this one is just fine. Mark it as OK. And then at some point it says, OK, no more bugs remain. All right, so this seems maybe a little bit like magic. So let me explain a little bit of how it works. So it combines basic program analysis techniques. Again, as with the previous speaker, this is straight up dependence analysis. It goes and takes the Excel spreadsheet, builds a dependence graph, and finds all of the input ranges and all of the formulas and understands where the data goes. And then it performs a statistical analysis. And let me explain what this statistical analysis does, because it's not what you might be thinking. So notice, like I said before, that 78 is not an unusual value. If you were to try to do outlier analysis on these inputs, it really wouldn't find it. Right? 78 is just an ordinary value like anything else. All right? What we do instead is we actually go and we look at the whole range. So here, for simplicity, I've included this as a giant range. A real spreadsheet obviously has a bunch of ranges, of exams and quizzes and so on. But pretend it's just one giant range being operated on. And what we do is we have this adaptation of a thing called the bootstrap technique. So I'm going to give you sort of an intuitive overview of what the bootstrap does. So the bootstrap is a so-called non-parametric technique. So instead of assuming that there's some distribution, like the normal distribution, which has these two parameters, right, mean and standard deviation, non-parametric techniques assume nothing about the data, which is great for something like a spreadsheet, because really it's unreasonable to assume that there's a normal distribution. So here's all of our inputs. And I've simplified this function. This is the function that determines the grade. And right now it says it's a fail. So what the bootstrap does is it repeatedly resamples from the original distribution to get new samples. All right? So what it does is it sort of randomly chooses one, then it randomly chooses another, and it makes a new sample. And we do this over and over again. So here is an example of a new sample, and you can see that in this case, this sample actually leads to a passing grade. All right? We do another resample. Again, we get a pass. We do another resample. We get a fail. All right? So this is the bootstrap, and it allows you to get a distribution that gives you a sense of how likely it is from the original data that you would have a passing grade or a failing grade. All right? So this is for all results. Then what CheckCell does is it actually partitions all of the bootstraps based on the original inputs, and it says, for example, here, what do the results look like if 78 is not present in one of those samples? And as you can see, this is very different than the one we showed before. Right? So this is the original sample that's with all of the data elements. And here we have this very, very unusual result. So the likelihood of this happening is very, very low. It's less than a 5% probability. So we say this is something that is really unusual. And then we rank things basically based on how unusual they appear to be and present those to the user. All right, so I'm not going to talk about the other things that CheckCell handles. It doesn't just handle numbers. It handles strings. It does all of this sort of ranking stuff. And if you're interested, I'd point you to our paper. All right, so the question you might ask yourself is, how well does it work? We collected hundreds of spreadsheets, and we ran CheckCell on them. The problem is that it comes up with all sorts of problems, but these are spidered from the web. We can't really go and say, hey, person who probably is unaware that their grade spreadsheet is on the web, we discovered a problem in your spreadsheet. Can you tell us about it? So instead, what we did is we took these spreadsheets and we injected errors into them. Now, anytime you hear anybody talk about injecting errors, you should immediately sort of ask yourself, wait a second, injecting errors, are you really injecting the kind of errors that people would actually make? And the answer here is yes. And I will show you how we did this. So how many people in this room have heard of Mechanical Turk? OK, good number, but a number of people haven't heard of it. So Mechanical Turk is a service that is provided by Amazon. And it's a kind of a very weird service. What it does is it allows you to go online and make money working on tasks that have been posted. These are things, it's like, here's a little job to do. And then you can hire people to do these jobs. So you can go to mturk.com later, after the talk, and check this out. So I'm going to show you a hit, what's called a hit. This is a human intelligence task. And so here's an example. So you can see that a typical hit will have something like this. Please enter the name of the product being advertised. This is the kind of thing that's not necessarily easy for a computer to do. Right? What's the product being advertised? Hipsters, correct? OK. So you entered the product, and then there's other choices. This is not an ad. The image failed to load. It contains adult content, et cetera, et cetera. You get 10 minutes to do this, which seems generous. You get a 6-cent reward, which seems less generous. But this is typical of the Mechanical Turk. So what we did is we actually took all of our spreadsheets, and we gathered data from them, and we generated, it's really hard to see here, but we generated an image with a bunch of different numbers. And then we paid people to actually just enter in those numbers. So because it was an image, they couldn't copy and paste it. They actually had to type in the numbers themselves. So we collected 169,000 retyped strings from these images. So people just entered all of these numbers again and again and again. And based on that, we were able to build up a typographical error model. And so we could actually apply it to any data, and the data that you get is typical of the kind of mistakes that people would make. Some transpositions, typos of adjacent characters, things like this. All right, so I'm briefly going to talk about results. We compared CheckCell to a straight-up outlier analysis that just looks for outliers in the inputs. And the way outlier analysis works is you assume some distribution, like a normal distribution, and if you discover that your results are in the tails of the distribution, you say that they're outliers. So briefly, the dotted line is CheckCell. The solid line is the Gaussian outlier analysis. The worse your error is, the better CheckCell does. The precision gets higher and higher with CheckCell and lower with the Gaussian approach. And as the error increases, recall also continues to stay high for CheckCell. And it's pretty fast. For most spreadsheets, it operates in under a second. For very, very, very large spreadsheets, like the Reinhart Rogoff spreadsheet, it might take a few minutes, but still completely reasonable. All right, so this is a screenshot of the Reinhart Rogoff spreadsheet. The red cell here is actually the very first cell that CheckCell reports as a problem. When we ran this on the Reinhart Rogoff spreadsheet, what I did, I actually ran into Michael Ash, who is one of the economists who did the study in a local coffee shop in Amherst. And I said, hey, Michael, we built this tool. We actually found out about the Reinhart Rogoff spreadsheet after we had built CheckCell. We said, hey, could we get the spreadsheet? And he said, no. They told us we couldn't redistribute it. So we contacted them and managed to get it. And brought him into our lab and said, OK, we're going to run it. Tell us if what we get are errors. So the first thing comes up. And I said, so how does that one look? He says, oh, yeah, Norway. So, OK, Norway. So it turns out that in their report, they point out that they had this crazy methodological problem with the way that they handled stuff in the spreadsheet. And it turns out it's a little hard to read, but Norway has an extraordinarily high impact on the results. And it's basically due to a statistical mistake. So they shouldn't have done this, and it created this tremendous problem. And it turns out that CheckCell actually reports 10 errors, and Michael confirmed that all of these are either typographical errors or significant methodological errors. So we declared victory. You can go ahead and download CheckCell at checkcell.org. So I would encourage you to do so. If you have Windows, I apologize if you don't have Windows. I don't use Windows either, but I run CheckCell in a virtual machine, and you can too. OK, so now let me move on to SurveyMan. So like I said before, surveys, like spreadsheets, are really ubiquitous. They're widely used. They're in industry for customer satisfaction, for example. They're used for psychometrics, for psychological studies, obviously politics, where they take the form of polls, government. This is actually a shot from the United States Census. So these are all kinds of surveys. So how are surveys developed? So this is a typical workflow. So somebody designs the survey. And the survey may have some flow, right? If you answer no to this question, you go to question 20, et cetera, et cetera. So you build up the survey, and then you go and you deploy the survey. So deploying the survey can mean online. It can mean going door to door. And then you have results, right? You ran the survey, you collect the results, and you're done, all right? So we view this, from a programming languages standpoint, as being akin to writing your program, running it once, perhaps twice, and then we're done, right? So hopefully this seems weird to you guys. Something is missing. Is anything missing? I assume that Technion does not teach its students to do this. So part of the problem here is that when you run your code and you run it once, probably it's wrong, right? So the Dos Equis guy knows this, and hopefully you do too. It turns out that surveys have bugs too. They're just a different kind of bug. I'm going to explain what some of these bugs are, but there's a whole range of different kind of errors that you can get in surveys, and soon the Dos Equis guy is covered in bugs, and that's just no good. And your results are invalid. So SurveyMan is a system that we developed for programming and debugging surveys. So the workflow is a little different. So you go and you design your survey, which we encode as a kind of CSV in a spreadsheet. We came up with this representation working with social scientists. Like I said before, social scientists love spreadsheets. So we said, well, let's bake this into a spreadsheet. They'll be happy with that. Then you can run SurveyMan. Either you can run it as a web server, or it can just deploy these things to Mechanical Turk. And then you get this sort of debug loop. And it finds these bugs and then reports them to the user. And then the user can refine the survey and make sure that the results that they get are actually valid. So very, very briefly, this is what a survey looks like. Again, you put it in a spreadsheet. You have these special columns. So question is just the name of the question. Options are the possible answers. The block thing corresponds to how they're ordered. And branching is if you say, well, I'm going to go, the answer to this one is 12, then go to this other part of the survey. All right? All you really need are questions and options. All right, so let me talk about these program bugs in surveys and what this means. So here is an example of a bug in a survey. It's called question order bias. All right, so these are all, by the way, surveys taken from Pew, which is a research organization in the United States. These are real surveys and survey results. So they posed a survey a few years back asking people, do you favor or oppose allowing gays and lesbians to marry? And you can see 61% said they're opposed. This poll wasn't taken in Massachusetts. And then they asked the second question, which is about civil unions. And here you can see that there was a reasonable amount of support for civil unions, 45%. They also asked this survey in the exact opposite order. So you can see that all of a sudden, by asking the civil union question first, the number of people in favor dropped from 45% to 37%. So this is something that you would not necessarily anticipate, right? You write a survey, you write the questions in some order, and you expect the survey results to not be affected by the order. But it turns out that the order can actually have an effect on the way people respond. So in this case, it appears that what's happened is that people are basically reacting negatively to whatever the first question is. And in this case, this is sort of a weaker version of the first, so people are more inclined to favor it. It's a kind of anchoring effect. So this is a pretty typical human bias that's something you would want to root out to make sure you had valid results, because your conclusions are completely opposite otherwise. All right? So here's another one, wording bias. So unsurprisingly, the way that you word a question can have a big impact on the way people respond. So this is a pretty extreme example. This is from a few years back, and this is a poll taken in the United States. Do you favor or oppose taking military action in Iraq to end Saddam Hussein's rule? I point out it was taken in the United States, not in Iraq, because it was 68% in favor. But when they changed the wording slightly, pointing out that if military forces are involved in a land war in Asia, somebody might die, then the number of people in favor drops. Right? So logically, these are semantically identical questions, but of course, the way that you word them can have a big impact on the way that people respond. Another big problem with surveys, is break-off or abandonment. So how many people here in this room have taken a web survey and not finished it? So you can see the problem. The problem is huge, right? So if you have a survey and people quit, that's no good. It can be a problem for a variety of reasons. So why do people leave? So one issue can be that the questions are problematic, right? So the questions could be vague. They could have not the answer you want, right? It says, what's your favorite ice cream flavor? Strawberry or banana? And you're like, chocolate. Chocolate's not there. Game over, right? They could also be offensive. So this is shockingly a real question that was asked in a survey that was about political ideology. Have you ever been unfaithful to your spouse or partner? And it turns out that there's a lot of people who, when they see a question like that, they run away screaming. They don't want to answer it one way or the other. So it's kind of, you would like to know this in advance if you could. And of course, another reason for surveys, for people quitting surveys, is this issue of abandonment. So if a survey is really, really long, especially as you get into it, you say, oh God, this is getting longer and longer, and you decide to quit. Right? So this is a real survey, obviously textual, that is given in the United States, the National Health Interview Survey. It doesn't look so bad until you find out that it's 20 pages long. All right? So again, you have a problem with people leaving. And I'm sure you've had this experience, and you're in a survey, and then the little progress bar barely moves, and you say, oh, Jesus, this survey's going to go on forever. All right? So these are all bugs in the survey itself. That is, the survey instrument itself has some problem. Right? It's too long, there's order bias in the questions, etc. But you can also have a problem with this kind of runtime of the survey. So these are bugs that we call bugs in deployment. So you have these, these geniuses out here who are doing these surveys, but I should also add, it turns out that you can also get paid to do surveys online, and it is a theorem of the internet that if you take pay and put it online, then you get bots. And it turns out that there actually are plugins for browsers to help you fill out surveys faster, which means randomly, of course, right? So this is a pretty serious threat to validity, right? So if you have people who are just clicking randomly, or they kind of lose interest in the survey and just click, or you have a bot, you're going to get survey results which are tainted. All right? So our goal is to actually get rid of all of these bugs, right? Get the social scientists to be able to produce results quickly and easily that are valid. So given this example that I showed earlier of the gays and lesbians and the civil union versus marriage, what we do is we actually allow you to, when you put these questions in, we will go ahead and test out all the different possible orders. So if you put these questions, this is going to be a slightly different example. If you put the questions in, by default, there's no order. If you want order, you have to say explicitly, there is a partial order among these questions. All right? So we're nudging people to get away from putting in these orders. So in this case, the question we're asking is, how often do you vote? And do you favor or oppose taking military action in Iraq? You might wonder if there's going to be an ordering effect. So when SurveyMan runs, it deploys a JavaScript payload to the browser. And every individual user sees a different randomization of the questions, subject to the partial order constraints that were imposed by the survey author. So for example, we have question A and question B that are before each other. Those are required to stay in the same position. You can say that this order is that way, but they can move around, right? They can float freely. All right? The same, and for other users and so on. All right? So here, we ask this dude over here, how often do you vote? That's the question A. Question A happens before question B for him. He says always, and then doesn't favor military action. And then we get somebody else, and the question order is different, right? So question order B comes first, they answer question B, then question A comes second, and they answer that. So once you do all this, you end up with distributions. So here is a distribution of ordering for question A before question B, or question B before question A, for the two different questions. You can see that in this case, the distributions are very, very different, and the distributions over here are about the same. So SurveyMan does a hypothesis test, and it says if this difference is statistically significant, it warns the user that there's some order bias. The similar sort of situation happens for wording bias. You, as a survey author, can actually put in two questions. So you can it's a little hard to see again, but it says, do you favor or oppose taking military action in Iraq? This is the one that asks, hey, maybe people will die. And what you do is you say, these are the two different questions. Here they have the same name. So this says that they're in position 1, and they're named A1. This means that they're logically the same question. So here, again, we ask these questions, and you have all of these different variants, A1, A2, A3, A4. This person sees A1. This person sees A3. And then, again, we build up distributions for all of the different wording choices. And if we see a big difference in the distribution, like here, for example, or here, we say there appears to be some wording bias. So how do we deal with breakoff versus abandonment? So it turns out that this ordering thing buys us a lot. Being able to go ahead and move things around lets us do all kinds of statistical tests. And one of them here is really easy to see. We can easily test whether the problem is people are leaving a survey because of a particular question or because the questions, they just got to a point where it's too long. So this person sees question A, question C, question B, and then they leave. So what we do is we say, well, they left at position 3 and they left at question B. This other person sees different order, question C, question B, question A. They also leave after 3. And we increment question A and the position. And then you end up with this distribution. So you can see that people seem to be leaving more and more by position, and not so many people are breaking off by question. You assume that the issue is really the position, right, and not the question itself. All right, so finally, dealing with these bots and with Homer, the insight here is that surveys, so if you have a very, very short survey, if it has one question, there's nothing you can do really to find out whether people are behaving randomly or not. But as surveys get longer and longer, they have more and more structure. The likelihood that people are going to naturally end up uniformly filling this huge space gets lower and lower and lower. So we basically adapt this insight, and we identify clusters inside the data. So by randomizing the order of things, we make lazy people and random people behave similarly, and then we discover clusters of people who are in certain spaces, and those are the good guys. So we score the survey results by how random people look, and present the results to the social scientists, and then they can decide their own filter threshold and say, well, this is really too random to be considered useful. So I'm going to briefly wrap up with a case study. We've worked with a number of different social scientists at my campus in linguistics, in labor studies. I'm going to talk about one that's completely weird and that turns out to, in fact, reveal a survey problem. So there's this notion of something called prototypicality. So prototypicality is this idea that people have in their head a notion of a sort of Platonic ideal for every concept. So here the Platonic ideal is a chair, right? So a chair maybe has a seat in your Platonic ideal, maybe a back, maybe legs. So this is a pretty unusual chair, all right? So the notion that this notion of prototypicality, some people believe, extends to all sorts of things, including numbers. So we have a sense of prototypicality, supposedly, of odd numbers. So odd numbers and even numbers, there's like really the ideal odd number and the ideal even number. And if you give people a choice, instead of saying, is this odd or even, and you say, how odd is this number, or how even is this number, then that will reveal their Platonic ideal for oddness or evenness. And so 787, it's pretty odd, not maybe entirely odd, all right? So perhaps the Platonic ideal of an odd number would have no even digits, for example, right? So that might be something you would think. So it turns out there was a big study on this, and it's like, oh my God, people have all of these notions of oddness and evenness, and it's so nuanced and fascinating. But it turns out that that's actually not the case at all. So we ran the survey with SurveyMan, and we asked different questions. And this question was, how good an example of an odd number is the number 463? And then how well does the number 463 represent the category of odd numbers? And it turns out, as you can tell, these distributions look very different, right? And it really is just the wording. And I think what happens is people are just like, how good of an example? 4, 6, 3? I don't know. 4 is even, 6 is even, 3 is odd. Maybe it's not a great example. In any event, it's really it's not a product of some deep-seated prototypicality issue, but really a problem with the survey. So to wrap up with SurveyMan, we've built this thing that lets you write a kind of survey program in a very user-friendly way. We actually have a Google Summer of Code student right now who's building a graphical web interface for SurveyMan to make it even easier. Now you get to debug your surveys and find problems in your surveys and get actually valid results that subtract out the random people like your homers and your benders. So to conclude, my group is really interested in adapting programming language techniques to address these problems of science, specifically social science, but really we're interested in science in general. We're using some very old tools, that is to say static and dynamic analysis techniques, applying them in very different domains, and using new tools like statistical analysis, especially aided by randomization. And this gives us the ability to do things like CheckCell and SurveyMan, and we're working on more stuff. I do want to shout out to my students, Dan Barrow and Emma Tosh, and some of my collaborators, Michael Ash, Sarah Kingsley, Joe Pater, and Presley Pizzo in different departments at the university. Our vision is to help debug science. I think this is something that's well within our reach. You know, programming languages are all about building abstractions and discovering issues with things, understanding them. We're really, really good at finding bugs in programs, and I think there's a ton of stuff out there for people to do. If you think about all of the studies that have been retracted because of statistical errors or other problems, this is something that I think we can do a ton about to make it easier for people to do good science and hopefully prevent fireworks from happening in southern Mediterranean countries. All right. With that, I conclude. Thanks for your attention.